Okay, welcome. All right, so we are going to continue our discussion of the Hubbard model today, and I think we'll finish and then go on to the next topic. So one thing I discovered after last lecture that actually my notes, the pages in my notes were out of order, and that's kind of why I got a bit confused in class as to the precise procedure of this super exchange calculation. So let me just now, of course, now they're in the right order and right order on the website. So just to quickly summarize, we are taking the Hubbard model as our basic model on any lattice. And we are interested in the regime where U is much bigger than T. And we are not too close from half filling, which is 1 electron per site. And in that limit, we want to work to second order in T and derive an effective Hamiltonian in the low energy subspace. And the low energy subspace will be the states which have, so that no site has more than 2 particles on it. So you never have to pay this extra energy cost U. So to second order in T, the dominant process is the super exchange interaction. And that can be understood by just considering, since you only work in the second order, just two sites. So if I have 2 sites in the Hubbard model, and let's restrict ourselves to the case where there's only 2 electrons total. So with 2 sites and 2 electrons, there's a total of 6 states. Here they are. What you notice then is that 4 of the states have energy 0 to 0th order in T. And 2 of them have energy U. So what we want to do is get rid of these states and get an effective Hamiltonian that acts only on these 4 states. All right, so then I told you about how you get the effective Hamiltonian by this canonical transformation, and there's a formula for it. And when you work out the formula, then you find that the new effective Hamiltonian from the formula from second order perturbation theory and in Cohen-Tanucci, what you find is that there's only a few. In fact, this is what I didn't say correctly last time. There's only 4 non-zero matrix elements of the effective Hamiltonian, which are these. So therefore, I have 4 states. I have a 4x4 matrix for my Hamiltonian. At the 0th order, it's all zeros because they have no energy. And at first order, at second order, there are 4 non-zero matrix elements. So it's very easy to diagonalize this 4x4 matrix. 2 of the states, the energy remains 0 to order T squared over U. And the other 2, you get this 2x2 matrix, easy to diagonalize. And you get energy 0 and minus 4T squared over U. That's really what I should have presented on Wednesday. And now you collect these 4 states together and look at the spectrum, and you happen to notice that this one state here has exactly the same energy as the other 2 states. It's 0. And that's not an accident. It's kind of required by spin rotation symmetry. The degeneracies have to be, since the total angular momentum is always an integer, the degeneracies have to be odd numbers. So therefore, there are the ground state has energy minus 4T squared over U. And there are 3 states whose energy, excuse me, is just 0. And also this procedure gives us the wave functions. So some of these states are just 1 and 4, and you can look up what the wave function is. And 2 and 3 form this 2x2 matrix, whose eigenvectors are just symmetric and anti-symmetric combinations. And so you can write down the wave functions of these 3 states in this projected subspace of 4 states. And now you look at this and those extremely familiar. These are precisely the triplet and singlet combination of 2 spins with spacing 4T squared over U. So you will get exactly the same wave functions and exactly the same energies if your effective Hamiltonian was written like this. They're exactly the same because they have completely the same spectrum, and also the wave functions. And this, so for this calculation to match this one, J must be 4T squared over U. Okay, so that's the canonical way you get this result. Alternatively, you can actually diagonalize the full 6x6 Hamiltonian exactly, which is what I did. I won't go over it. There was a mistake in the notes. This was a triplet, but actually it's only a singlet. I corrected it on the website, and you get the same answer. All right, so that's kind of where we were. Any questions? All right, so now what we have is sometimes called the TJ model. And this is, believed by many people, including me, to be basically what all you need to understand the physics of the high temperature superconductors. You take this model on the square lattice. You almost certainly do need second neighbor hopping, not just nearest neighbor hopping and second neighbor exchange, but we forget that here. So we assume everything is just nearest neighbor. Now this Hamiltonian acts on a complicated Hubbard space. Previously the Hubbard model, the Hubbard space was easy to describe. It was just all the possible states you could make on a square lattice with a fixed number of electrons. You just take all possible states with electrons, spin up, spin down on any site. Any state is a legal state. And that gives you the full Hilbert space. The total number of states, if you think in the grand canonical ensemble, is 4 to the n, where n is the number of lattice sites, because on each site you can put an empty site, spin up, spin down, or doubly occupied. Okay, so now we have the TJ model that acts on a reduced Hilbert space because we have now gotten rid of all the excited states which were doubly occupied. And so now on each site, there are 3 states allowed: empty, spin up, or spin down. So the number of states, you've improved your life a lot. You've gone from 4 to the n to 3 to the n, which is a much smaller number when n is very large. But you've paid a price. You paid a price is that this Hilbert space is not easy to describe. It cannot be just built out of free electrons, because you just have to remember, to know whether a given state is legal for a given electron, you have to know what the other electrons are doing, because you can't put 2 electrons with opposite spin on the same site. So whether you're allowed to put an electron on a given site or not with a given spin doesn't just depend on the Pauli principle. It depends on knowing more than the Pauli principle. It depends on knowing the upspin electrons have to know whether there's a downspin electron or not. So it's a correlated space. So it's really a Hamiltonian acting on a very complicated correlated Fock space. And that's why it's hard to work with. I should say that also, so sometimes you write the fact that you're acting on a correlated space by putting some projection operators, which I wrote last time, but I won't now because it just makes the picture messy. And there's another term where you generate higher, longer range hopping, which I didn't write down either. Okay. So these are the most important term in the limit that you're close to half filling, which is where you find the phenomenon of high temperature superconductivity. All right. And J is 4T squared over U. So by definition, J has to be much smaller than T. So this J is much smaller than this T because it's T multiplied by T over U, and T over T is much smaller than U in the derivation. But often people just look at this model even for J of order T just to see what this model says. But even for J much smaller than T, this is not an easy model to solve because you can't do perturbation theory, because of the projection operators. Even at J equals 0, this is a non-trivial model because it's got this constraint on the Hilbert space that it acts on. Okay, so there's a lot of technology that people have developed to to describe this kind of system with constrained Hilbert space. In particular, there's this whole trick of fractionalization and gauge theories that people use to describe the physics of the TJ model. Well, I don't think I'm going to cover that in this course. I may say a little bit about it towards the end. But for now, we're going to do the simplest thing, since we've just learned about superconductivity. We're going to ignore all of that. We're going to indeed treat this term J as a correction. And even more, we're just going to treat it in Hartree-Fock theory. Well, really, Hartree-Fock BCS theory. If you did Hartree-Fock, you can look for various types of magnetism. You will find antiferromagnetism at half filling. If you did an honest Hartree-Fock analysis of this Hamiltonian, just pretending that this Hamiltonian acts on the full Hilbert space of free electrons. So once you start pretending that, then it's possible to do a lot of all the things we have learned without any further worry. Okay, so we are pretending that we ignore the constraint, and we are not interested in magnetism since we're interested in superconductivity, in particular high temperature superconductivity. So what we want to do is to factorize this term just like we did for BCS theory. Okay. And the main thing that I want to get across today is that, so this is a model with purely repulsive interactions that we started with. And after we did this canonical transformation, we got the spin exchange interaction nearby. And what we will show is that this spin exchange interaction can be effectively attractive, even in this model, in not the usual BCS state, but in sort of extended BCS states where the Cooper pairs have non-zero angular momentum. So right now, the Cooper pairs that we looked at were effectively S-wave Cooper pairs because there was no dependence on the pair wave function on the angle between the two electrons. But now we'll see that if you allow for higher angular momentum pairing, then this interaction can actually be attractive and lead to pairing. And most people believe that's the basic physics of high TC superconductivity. Of course, mean field theory is bad and we can't actually get numbers from it, but that's rough, to zeroth, I would say, yeah, to zeroth order, that's what's going on. And I think there's a lot of evidence. So let me just present the zeroth order theory, which of course has committed already many sins, including treating J perturbatively and forgetting about the constraint on the Hilbert space. All right. And also the other comment is, of course, angular momentum has to be interpreted correctly. Angular momentum is a meaningful concept only in the continuum, and you have rotational symmetry. When you're on the lattice, you only have, four-fold rotation symmetry. You only have four angles, not you have a discrete rotation symmetry, not a continuous rotation symmetry. So you have to look at eigenfunctions of that rotational operation on the square lattice, the discrete rotational operation. And that's what you mean. So these are eigenfunctions that are not the simplest trivial eigenfunctions. If you know a little bit of group theory, then there's a set of representations of the square lattice space group, and so this is a non-trivial representation. But people just use the words, at least I do, because they're a lot clearer than the real notation, which has horrible names like A1G and B1G. I never remember what that means. So we just call the angular momentum pairing SPDFG because, well, you approximate. You can roughly think of a certain representation of square lattice as like a D wave, as you'll see in a minute. All right, so what we're going to do is just take this interaction and decouple it in the BCS channel. So I could just, if I go back to how we, what I have to do is take SI dot SJ and honestly do a calculation. I have to go back and where did it go? just do the all possible decoupling trick. Where is it? It was before the BC. Well, yeah. So what I honestly have to do is to take the SI.SJ interaction and apply this completely. Do all possible decouplings, and then see what you get. So we agreed when we did the BCS theory that we throw out this part because that's the Hartree-Fock terms. And again, I agree, let's throw those out. Then you have to look at this. But even in this context, this becomes more complicated, and I won't fully treat it, as you'll see, but at least in the beginning. And then I'll also say a little bit about what happens if you just even did this line perfectly honestly. Okay, so let's go back. So I'm going to follow a procedure which I guess was due to Bhaskaran and Anderson first, where they showed, they argued in very simple terms how this kind of interaction could lead to pairing. They actually got the wrong symmetry. They in fact said S wave, and I'm sure they regret it. But the fact that the antiferromagnetic interaction leads to pairing was actually already known earlier in the context of the heavy fermion compounds. Okay, but let me just present the argument by Bhaskaran and Anderson because it has certain appeal. So I just take this SI.SJ and I write it out in its full glory. And so then I'll get a Pauli matrix from the first S and a Pauli matrix from the other S. So I have a product of two Pauli matrices with indices alpha, beta, gamma, delta, which are contracted with the indices on the electrons. Okay, and I have to sum over all directions, the sigma x, the sigma y, and the sigma z. Okay, so here we use an identity which you can check for yourself. So this is exactly true. This identity here, sorry, that's been pushed up because, well, anyway, this is when I was editing it before an iPad. So it's -2 epsilon alpha gamma epsilon beta delta. So you pair the first index with the first index and the second one, you put an epsilon tensor. Epsilon is the antisymmetric tensor, so that's just epsilon up down is minus epsilon down up is 1, and epsilon up up and epsilon down down is 0. Okay, so you can check by taking, well, literally how many values are there? There are 2 times 2 times 2 times 2, 16 possible cases of this formula. And you can check that the left-hand side is equal to the right-hand side for all 16 values of alpha, beta, gamma, delta. Okay, that's a fun thing to check, and it works. All right. So now I plug this this formula into S1.S2. So I have two sides, S1.S2. So this is what I have. The sigmas are just numbers that I pull out and I apply this formula, and then applying it, I get this. So I get -j/2 epsilon alpha gamma C dagger 1 alpha C dagger 2 gamma, and the combination conjugate, and then I get this and this. Okay. So now we notice something interesting. This first term especially has a really neat form. So what is this object? So if I create the state here, which is epsilon alpha gamma C dagger 1 alpha C dagger 2 gamma acting on the vacuum. Well, it's the state which is, we can write this way. It's like a singlet pair or a dimer. It's basically the state. Okay, no 1/√2. It's up down minus down up. Okay, so this is a singlet pair of electrons that it creates out of the vacuum. And so what is this operator? It's just basically the Cooper pair operator. So this, I could think of this as a Cooper pair on a bond of the square lattice, or link of the square lattice is a better word. link. So if those two sites were empty, then this object creates a Cooper pair, singular pair of electrons on that site. Okay, and so then this object here is like a, this one annihilates it and this creates it. So it's like a counting operator. It counts the number of Cooper pairs. And every time you count a Cooper pair, you pick up an energy, well, some negative energy minus J/2. So it's like that if there's an attraction between the electrons and they want to form Cooper pairs, because then you gain energy minus J/2. So you can really think of, in this language, roughly speaking, the exchange interaction, at least locally, as an attraction between the electrons. Now, there's one thing you need to worry about. Of course, our previous Cooper pair, had opposite pair of electrons at all distances, including 0. They were also allowed to be on the same site. So there is an infinitely strong repulsive interaction on the same site for the two electrons, but at least the nearest neighbor part is slightly attractive. So now it becomes a question of, is the repulsive interaction going to win, or the attractive interaction on nearest neighbor pair is going to win? And that really actually depends on what particular lattices you're on, and the answer is slightly different. Exactly how, which wins under what conditions. But one thing you can see right away is, suppose I now take this pair and give it non-trivial angular momentum. Now, one thing you should remember from your quantum course, anytime a particle has non-trivial angular momentum, the wave function vanishes as they approach each other. So it's good to have non-trivial angular momentum, because then you'll never experience the local repulsion. Okay, and that's roughly the reason why you end up picking a non-zero angular momentum state. But okay, sometimes you don't, and I'll also mention, and like in the iron pnictide materials, you don't, and that's for complicated reasons, which I'll briefly discuss. Okay, all right. So this is giving you an attractive interaction, and that's really, I'd say the basic physics of high temperature superconductivity. Of course, we want to do much better, but doing much better than this is really hard, at least in the large U limit. Okay, so now so what are we going to do this term? We're just going to apply BCS. We're just going to replace one of this by an expectation value, or this by an expectation value, and that's all. We should also factorize this, and that gives you small corrections to what I'm going to discuss, but let me not do that for now. I just throw this term out. This is like a density-density interaction, and close to half filling, this is just one on every side. So let's not worry about that. There's an attractive term that we care about. It's also smaller, so let's throw it out. Okay. All right, so now when I factorize that, I finally get a Bogoliubov Hamiltonian right here. This is, I'm keeping track of the overall energy too. And then this delta ij, so now is basically the expectation value of the other operator. So this is exactly what I did for BCS theory, except I'm now working in real space on a lattice rather than a momentum space. Okay, so now my Cooper pair, my variational parameters are, for every link of the lattice, I have a delta ij. Okay, so I have some lattice here. On every link of the lattice, I'm decoupling, and on every link I have a delta, and on the horizontal and vertical links. And in principle, all of them are independent variational parameters. So if I don't assume any symmetry, no translational symmetry or anything else, then I have an infinite number of variational parameters, which I now have to choose. I have to choose the delta ij to minimize at a given density of electrons, this energy. Okay, that's exactly the calculation I went through with the Bogoliubov theory. Now just the indices and the momentum space structure is a bit different. All right, so first of all, let's just assume translational symmetry anyway. That is, this delta should be the same as that delta, should be the same as that delta. So all the horizontal deltas are the same, and all the vertical deltas are the same. But I'm going to hold off putting the horizontal deltas equal to the vertical deltas. Okay, so we're going to take our delta ij to be only functions of the difference between the sites, and not and real. So basically, there's no orientation to them or no phase that matters which way you go. And so there's only two real numbers left over, delta x and delta y. Okay. All right. So now let's just put, so that's our assumption. You know, these are some numbers that went into this theory. So now I just put in delta x here, and delta x squared here, and the same for delta y. And then I do the Fourier transform of everything. So then it becomes quite simple. These are nearest neighbors. So if I is a given site, j must be next to it. So if I is here, j can be here, 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 or here. And for each one of those, I'll get a delta x. And then I just do the sum and the Fourier transform. And when you collect all the terms, what you find is this Hamiltonian, okay, right here. So the delta x squared and delta y squared. And then now it's looking very much like BCS. It's almost exactly the BCS Hamiltonian I had a couple of lectures ago, the Bogoliubov Hamiltonian, excuse me. C dagger k up, C dagger minus k down with some delta. But now the only difference is this delta depends on momentum. Previously, this was a constant. Now it's a function of momentum. And it's not any old function of momentum. Because I have nearest neighbor pairing, you see that delta k is this function here. Delta x cosine kx plus delta y cosine ky. Now, if I had on-site pairing, suppose I had on-site pairing, which we don't, then there'll be a term like delta 0, which will be a constant. This will be on-site pairing. So what we did when we did the BCS theory was something slightly different. We assumed that the pair wave function was really big. It's of order the Fermi velocity divided by the Debye energy. We assumed the pair wave function was very big, and so the k's there were very small, and we just replaced the cosine k by a constant. So we just ignored the k dependence of delta k, and that's equivalent to assuming that the Fermi wave functions are really big. But here we will keep track of the k dependence, because it's only from the k dependence that we're able to not worry about the huge repulsive energy on site. We don't want any component of our wave function to be 0 exactly on site. All right, so that's really the only difference with this k delta k here and delta k star. And then you also have the self-consistency condition, which was here. Also, one difference from BCS theory is, when I did BCS theory, I absorbed the factor of j into the delta, and now I just keep it here and not here. So now there's no j here. Previously, there was no j there, or u. I called it u there. Okay. So now you have this attractive interaction on a link, and that gives you the BCS theory again with a minus j here. This minus j comes from exactly this minus j over 2 over here. This minus j over 2. You get rid of the factor of 2 because there's 2 terms in here from the epsilon tensor. Okay. And I really carefully checked all the factors of 2. All right, so then what? So you have this. This is a Bogoliubov Hamiltonian, exactly as before, except delta is a function of k. And then I have a then delta k is equal to this function of delta x and delta y, and delta x and delta y are equal to this expectation value, which after taking a Fourier transform becomes this. And now these are the same because of the symmetries of the pairing. And now I can combine this to get this. So now this is my equation that I have to solve to determine delta x and delta y. This is my equation for delta x. This is my equation for delta y. And what is the right-hand side? Well, the right-hand side I can evaluate from the Bogoliubov transformation in terms of the UKs and VKs. Now here I'm assuming I'm at 0 temperature. So I only need to keep the facts on gamma, gamma dagger, because there are no gamma particles in the ground state. So you have to add a gamma particle and then remove it. You just get 1. So that gives you this. And so here it is. So these are the final equations I have to solve. So these are the gap equations. And I have 2 equations for delta x and delta y. And they're just the complete analog of the BCS equation, where I had only 1. And basically, you get the BCS equations by replacing this J by a U, putting a restriction on the summation to within the Debye energy, and dropping all the cosines and putting them equal to 1. So basically, it's exactly the same equation, except there's all these form factors, as we call them, sprinkled in there, these cosine kx's and the cosine ky's. Okay, so now we want to solve these equations, and hopefully there is a solution, and we want to pick the lowest energy solution if there's more than 1. So, so that it actually do turn out to be often more than 1 solution at 0 temperature. And so then you have to find which has the lower energy. And that actually turns out to be quite a subtle calculation, which one has a lower energy. It's not at all obvious. And in fact, Anderson and company got it wrong in the early days. I think it was Kotliar et al. Who first did it correctly. So what is the issue here? So first of all, I said, well, let me not assume rotational symmetry. So when I drew this picture, I said, let's allow delta x equal to delta y, and both real. Be different and real. Now you would say, okay, that's a problem because now I don't have a symmetry of rotations. I can't rotate the lattice, and this will show up. If really delta x was different from delta y, the lattice would look longer in that direction than this one. It'll be a rectangular lattice because it has different pairing in the 2 directions. And we know that's not what happens. At least it does happen actually, but it's very, very weak. So the naive guess would be delta x should be delta y. But that's not the only guess that's allowed. If you think a bit more, there's one other choice, which is delta x equal to minus delta y. And that's, in fact, the correct choice for the cuprates. It's called D-wave pairing because, roughly speaking, if I look at the dx squared minus y squared wave function, you may remember that dx squared minus y squared, well, that's just x squared minus y squared over r squared. This wave function changes sign when you rotate by 90 degrees. So that's why it's called D wave, not literally that it's actually this function. There is a better name for it in the crystallographic terminology, but I don't remember. I think it's B1G or something like that. Anyway, so turns out delta x can be minus delta y, and that doesn't break any symmetry. In fact, you have to do a very, very careful quantum interference experiment to detect it, because delta by itself is not measurable. You can only measure the correlation functions of delta. It doesn't conserve the number of particles, so it's not a measurable quantity. So the phase of delta is free for you to to choose. Now you could choose other phases, but if you choose some other phases, then you find that you break time reversal symmetry, or you can just gauge it away. So the only gauge invariant choice that doesn't break any symmetry, including time reversal and lattice rotations, are these choices. Delta x equals delta y, and delta x equals minus delta y. I forgot the most important sign in this slide. Yeah. Okay. So now delta x equals delta y seems like an S wave. It's the same in any direction, but it's sometimes called extended S wave. And the reason it's called extended S wave is because this delta zero is not present. I don't allow for anything that's independent of k. And the reason you don't allow that is because you don't want the pairs to be on site. You want the pairs to be always on the bonds. And then, the Coulomb energy cost, you don't have to worry about it. So if you allow for extended S wave and D wave as your pairing solutions, so extended S wave, there's no symmetry then that distinguishes extended S from S. As far as the group theorists is concerned, they're the same. But to physicists, they can be very, very different because the wave functions are, look very different. One of them vanishes at the origin, the other one doesn't. Or the first one, of course, it doesn't quite vanish, but has very small value at the origin, the S wave. This one exactly must vanish, at least in the continuum. All right, so to physicists, these are, both possibilities, extended S or D. And which one's going to win? Well, you really have to do a more careful calculation than I have described here. It's not easy to tell. I'll give you a kind of a hand-waving argument pretty soon. But what we now know, you just take this calculation and work it out. And you work it out for different EK. So if you work it out for EK corresponding to the cuprates, then you find that the lowest energy state is the D wave state. This wins for cuprates. So for the cuprates, D wave is the correct solution. But for the iron pnictides, iron selenide and other materials, the answers are very complicated depending where you are, because you also have multiple orbitals on each side. But there seems to be quite a window where this is the correct answer, extended S wave. So, okay, I've covered, I don't know how many, 20 years of arguments very quickly there, at least in the simplest form of it. What's the origin of D-wave pairing in the cuprates, and what's the origin of extended S pairing in the pnictides? This is the simplest bare bones argument. Of course, if you want to do any better, then you need lots of computers and lots of confidence in throwing out the Hubbard repulsion on the on-site. Okay, but all right, I think it's a good argument. All right, any questions?
I was wondering, so these Cooper pairs, they live in position space rather than in Fourier space? Oh.
Well, I mean, you could take them in either space. In both cases, in one is just the Fourier transform of the other.
I meant, like, can we think about it like just singlets? I mean, two fermions which form some pair in position space, and we have like a liquid of these dimers.
Yes, yeah. yes.
Okay.
So the difference, whenever you have, you can think in either position space or real space. I mean, this is very general. This kind of pairing between any two sites I and J is also present in the. So let's just call this delta IJ. This is also present in the old BCS superconductor. This is also the case. All right. So first of all, just if I think in terms of this, the first thing, there can be a center of mass momentum with, if I think in the continuum, there's a center of mass momentum where they move together. That means if you have any center of mass momentum, there'll be some variation as you move the center of mass. That we throw out. We say, let's look at the zero momentum pair where the center of mass momentum is zero. That's what we said in the BCS theory. In the present theory, that's exactly this. This is exactly the statement, the same statement. This is just in the lattice terms, exactly the same statement. No center of mass momentum. This is the same statement that things don't depend. Things only depend on I minus j, on relative coordinate, not the center of mass coordinate. Okay, so now you have a delta of I minus j, and you can plot delta of I minus j. It's a function of I minus j. This is very schematic. Let me make it distance. Make another curve. So what we find for, at least in this theory that we are discussing, we are now claiming that in the cuprates, this is a delta function at 1. And it's 0 everywhere else. Okay. So this is TJ model. And what BCS theory said, well, for BCS theory, it's a very smooth function. It's a function that's okay. It's so long range that I can just draw it in continuum. So in the continuum, it looks something like this. It falls off in some distance. This is a distance of order called the coherence length. And this coherence length, if you work it out from the BCS theory, it turns out to be h bar VF over the gap. Okay, so it's a long thousands of angstroms. And the wave function is non-zero everywhere.
So it looks it looks like some BC limit, right?
What?
I mean, BC limit.
Yeah. Okay. Actually, no. I think I didn't say this. BC limit. Oh, yeah. Okay. No, the red curve. Actually, I didn't say that right. Yeah, okay, let me yeah, okay, there's a subtlety here. I didn't quite say that right. So this is delta ij. Let me just say I'm restricting myself. Yeah. No, let me erase all this. So. Yeah, so right. So what appears in the Hamiltonian is, you know, delta this quantity delta k, which is delta x cosine kx plus delta y cosine ky. This is what appears in the Hamiltonian here. Whereas in the BCS theory, what appears in the Hamiltonian was a constant, strictly exactly a constant. Okay, but now I can try to compute this quantity, and take its Fourier transform. And so let me try to talk about that. So now I plot delta of I minus j. Which is I minus j. And actually this quantity, if you compute it in the BCS theory, yeah, so it looks something like this. Yeah, let me. Yeah, so what I said about BCS was correct. It falls off is a length scale C, BCS, C BCS is H bar VF over delta. So this is for BCS theory. But for a D wave, it looks slightly different, at least in the cuprates. It vanishes at the origin because of the angular momentum part. And well, okay, those are discrete numbers, but let me just draw some continue. And so it looks something like this. It has a much smaller coherence length. So the point is that the Hamiltonian, because the interaction is nearest neighbor, this interaction is nearest neighbor, it only cares about the pairing amplitude on nearest neighbor sites. Okay, but if you take this full Hamiltonian and you compute this quantity on the right hand side, take its Fourier transform, you know, if I so the delta this yeah, so let me write that out. Yeah, so this delta ij is equal to, in this center of mass frame, sum on k, ck minus k up, ck down, times e to the ik of ri minus rj. So what you have to do to compute this quantity is take the Fourier transform of this. You have to take the Fourier transform of this function of k, and that's not a that's not just purely nearest neighbors. So in this theory, actually, the pairs are longer range. But the energy only cares about the nearest neighbor amplitude, but the pair is slightly longer range. But because it's D wave, it vanishes when they approach the same side.
Okay, yeah, thank you.
Or extended S wave. Okay. Great.
Sorry, I have a follow-up question to Alexander's question here. So I think he mentioned that at some point asked this question, like, can we think about it as essentially as dimers, like just like a dimer covering of the whole like square lattice? Just from this picture.
I mean, that people work on such models where they take dilute gas of dimers on the square lattice, and they write down an effective Hamiltonian on the dilute gas of dimers and get superconductivity. That's not what we're doing. We're really dealing with free electrons with pairing. Okay, so the way to think about it is that we're really talking about just a free electron state. We start with a free electron state, and that's of course the most questionable assumption in this whole calculation, that we just start with the free electron state, and then we assume that the free electrons have an attractive interaction every time they are nearest neighbor sites and have opposite spins. That's the problem you're solving. Suppose I gave you a problem where there was some strong repulsion on site and an attractive interaction where two electrons were nearest neighbor pairs. That's all. The dimer is a strong coupling picture that
yeah, I see. So in some sense, like this dimer term in our case is, yeah, this dimer term in our case is the perturbation essentially.
Yes. So,
right.
Well, I mean, here we go. Yeah. So this dimer term, excuse me. I mean, it is small in the sense that, even generally, in the sense that J is smaller than little t. This J is smaller than t. But what's not small, and what's a very strong effect which we're throwing out, is that the Hilbert space is not the Hilbert space of free electrons. There's an infinite term that we're throwing out. Okay, if you want to keep that infinite term, then you end up with the dimer model, which we're not solving. That's a whole another game.
I see.
Okay.
I see. Yeah, but I had another question that was like, I just wanted to make sure that I understand the difference from the original superconductivity. So in the first,
yeah,
in the original one, we had attractive interaction that was like non-local and mediated by phonons.
right.
But here we are just writing electrons on a lattice with like on-site repulsion, infinite on-site repulsion. And somehow I don't understand why like one of the models would apply, you know, to one material. Like, could you explain in terms of like these materials where we observe superconductivity, why is like this high TC, you know, materials, this TJ model applies, and in the like Nobium or something, the BCS model applies?
Well, I mean, because the microscopic structure is that you, the Hubbard model is a reasonable starting point for the cuprates, but it's not for niobium. You can just look at the micros, the band structure and the orbitals and so on, and you find the Hubbard model is not a reasonable starting point for niobium. Excuse me a minute. I don't know. Just get some more water. Can you hear me? I think
Yes.
so, right? Yeah, I've been just talking too much on Zoom. My voice is giving away. Right, so the Hubbard model is not a reasonable starting point for niobium, but it is for the cuprates. You just look at the band structure. But the Hubbard model is very difficult, and so we try to get the TJ model when U is very large. And now we're doing something that's totally unjustified. I mean, I just have to admit it. We're just ignoring the infinite U on site and just looking at this as a perturbation to the free electron problem. And we can do similar things for the iron arsenides also. And you get, in fact, the correct answer in both cases if you do this procedure. Now I can, you know, it would take me, there's a lot of reasons why and methods where people can justify this calculation, but right now I have not justified it. So in the end, I'm just taking free electrons with some sort of attractive interaction. For the case of the BCS theory, we just took a very long range attraction, but very weak attraction of some strength U naught. Here we are taking nearest neighbor term, which is attractive to opposite spin electrons, because opposite spins can lower the energy by forming a singlet. So that's all. So the problem we are solving right now is what happens when you have nearest neighbor attraction for opposite spins. And I showed you by this, the purpose of this transformation here was to show you that the effect of this coupling is the equivalent to an attraction, which is nearest neighbor. Okay, so you took that nearest neighbor interaction and you solved it, and you find these pairs which have different sizes. Here, of course, we don't have a Debye energy, so the pairs are fairly short, and that's what you see in the experiments when you measure the coherence length. But if it's D wave or extended S wave, they vanish when the pairs approach each other, which is a good thing. So just the fact that they vanish, they approach each other, gives us hope that neglecting the on-site repulsion was not such a bad approximation.
So I have a question about like how we interpret the phase and phase coherence specifically.
Yes.
So back in BCS, I was able to, kind of convince myself that because the gap does not depend on the phase, then the system can just kind of spontaneously settle into some phase and demonstrate phase coherence. Can you comment maybe on phase coherence in these D wave systems? So does the system still demonstrate phase coherence, and then does the gap energy vary like based off what phase it spontaneously chooses?
Right. So there are two different phase variations you have to think about, and this is really a great question. That's really crucial. So let's go back to BCS theory. When we first did the BCS theory, there were two things. We had this delta parameter, and which is the pairing of two electrons, the Cooper pair wave function. That has two different types of variations. There's a variation in the center of mass, which we said was a constant. So there's no variation. And then the variation on the relative coordinate, and that gives you a phase in delta of k, some e to the I theta of k, I think I called it. And then we minimize the energy, and you found that theta of k had to be the same for all k. So here also, in a very general theory, we have a delta of, you could imagine taking a delta x and a delta y of k. And here, in fact, I just assumed that they're not functions of k because of the nature of the way I did the BCS theory. But here also, in the BCS stage tells us that the delta x and delta y are basically the same at all momenta, okay, but they have opposite signs. So this particular phase, the relative phase of the x and y bonds is fixed to be pi, no matter what, under every conceivable condition that you do an experiment, say on the cuprates. However, there's another phase, and that's the phase you always measure. That's the phase I talked about when I talked about the stiffness of the London equation. And that phase is the center of mass phase, okay? So you could have another phase here. So if I go back to this delta ij, I could imagine that delta ij is some function of delta of j minus a, and I could put a e to the I, some phase here of I plus j over 2. Okay. This is the phase that you are measuring in any experiment when you talk about phase coherence. Okay, so there's an overall phase that applies equally to the x and y components, which depends on the center of mass coordinates of some region, okay, of electrons. That phase it's the same everywhere in a perfect superconductor. When it's carrying some current, that center of mass phase, this is the phase that has a gradient. This one that depends on the average of the coordinates.
Okay, I see. Thank you.
Okay.
Yeah, that was confusing, but that clarifies it.
Yeah. So in the previous chapter, when we talked about helicity modulus and all of that, the phase in the helicity modulus that I was twisting was this one. Okay. It wasn't the one that depends on the relative coordinate. That's rigid. So in a D-wave superconductor, it has opposite signs. So in fact, to measure the difference between delta x and delta y, you have to do a very clever experiment where you somehow tunnel in only in the x direction and you tunnel in only in the y direction, and you do some interference between them, which is the experiment that was done by Kirtley et al., which established very clearly that this was a D-wave superconductor. But when you take a cuprate superconductor and put it in a squid, and it's got some phase variation, the fact it's D-wave makes no difference. That is simply that variation of the phase in a squid is the center of mass phase. Okay, I'm out of time. Anyway, I had couple more slides answering the other question. How could I tell by just staring at, say, the EK and knowing something about the interaction, what pairing symmetry is going to be? Generally, you can't, but sometimes you can make a good guess. And I guess I'll tell you that argument on Monday. Okay, any other questions? Okay, then have a great weekend. And the problem set is due on Monday. I gave you a little extra time to go to the March meeting. And yeah, see you on Monday. Oh, and of course, tomorrow, hopefully I'll remember, 9 a.m. is the discussion time if you want to continue to discuss some of this.